applications which we are working or which we are interested in IBM Research Lab India, which is one is retrieval augmentation, augmented generation, and another is how to incorporate or increase the tool calling or function calling abilities of LLM so that they can uh, be more useful in agentic tasks. So before that, I'll start with the basics of large language models. So I wanted to cover these. I don't know what is the background of the audience exactly, but I wanted to give a brief a primer like when we say large language model, what exactly it means and how they work in general. So if you have seen traditional NLP system, let's say you want to build a sentiment classifier where the goal of that classifier is given a sentiment, let's say of a movie, you need to classify whether that's a positive sentiment or a negative sentiment. So somebody writes reviews on the IMDb, you need to automatically classify whether that's a positive or a negative review. So generally, how to design those kind of a classifier is collect large labeled examples where uh, X comma Y pair, where X is the um, sentiment or the whatever review people have submitted, and Y is the label, like whether it's a positive or negative. So you collect a lot of these examples, either by IMDb or on, let's say you want to design for Amazon, so collect it from there, or put a human maybe and create some labeled examples. And generally then um, choose a model like an SVM or maybe a neural network based model and train that model on those data and create a sentiment classifier. But a powerful paradigm comes around 2020. It's an old thing, but yeah, it came into deep learning, which is transfer learning. So rather than just training this sentiment classifier, what people were doing that you take a huge neural network, let's say a big neural network. I will say what I mean by a huge or a big neural network, and you do a self-supervised pre-training. So you don't do supervised training now. You do a self-supervised pre-training. So what I mean by self-supervised, so it is done on unlabeled corpus. It's not done on labeled corpus like X comma Y pair. So you are doing this, let's say, pre-training on Wikipedia, for example. Wikipedia text. So a large amount of text you collect from Wikipedia and you do a self-supervised pre-training on that large corpus. So so you create certain auxiliary tasks using that data, unlabeled data. For example, you mask certain words and you ask language model, predict that word. So you know that word. So it's like you take an unlabeled corpus and create those tasks like mask certain word and ask LLM to predict those words. You don't require any labeled data, but you create this labeled data on the fly and you do a pre-training of, let's say, a deep neural network or a neural network. These are generally known as auxiliary or pre-training tasks. So once you do that pre-training, the models learn a lot of capabilities about languages, about certain tasks which is present in the corpus. And then let's say you want to design now your sentiment classifier and you want to increase that accuracy. So now you collect only few labeled examples from, let's say, IMDb, and then take that huge pre-trained model which you trained, maybe add certain more layers on it, or maybe freeze most of the part of the supervised model, just unfreeze some of the layers. So either you can add new layers or you can freeze certain layers or you can unfreeze certain layers. And then you do a supervised fine tuning on this. So this is how the paradigm shifts. So rather than just relying on the supervised data, people realize that there is large amount of unsupervised data is there. You train it on that data, make LLM aware of several capabilities, and then maybe if you want to fine tune on certain things, then you fine tune on your desired task. So this idea of pre-training is very powerful, and it becomes the you can say the backbone of large language models emergence. One more thing, if you have any question in between, please feel free to ask, like in between. Don't wait till the end or anything. So how does so I want to give an example of a one pre-test or auxiliary task, which is language modeling, which is very like which is used for training like models like GPT-4, or if you heard about Meta's Llama 3 and Llama 4 models. So most of these auto-regressive models are trained using this uh, language modeling or pretext auxiliary task, which is known as language modeling. So what is the task of language modeling? It's a very simple task. It's the task of predicting what word comes next. So let's say you collect a corpus from Wikipedia and it has a sentence, haven't seen you in a while, and I hope, let's say, I hope was the word here. We mask it here and we feed this to our neural network and ask what should be the word in this position. We know the word should be hope, but there are multiple possibility. The LLM will going to predict a probability at this position for all the words in the vocabulary. So every LLM has a vocabulary and it predicts the probability over whole vocabulary. Let's say there is a vocabulary of 64,000 words, and let's say LLM predicts probability of all those things here, and you compare what is the probability of word hope, because you know that hope was present in the corpus, and you calculate the cross entropy loss and you back propagate. So this is how the models are pre-trained using language modeling task. Mathematically, if you want to see the task of language modeling, you can model like that. Given a sequence of word, prefix words, x1 to xt, what is the probability of the next word? And then you apply cross entropy, compare with the ground truth, and back propagate. So this is the simple language modeling task, and most of the powerful language models are trained using this simple language modeling task. So now, once you pre-train those models on huge corpus using language modeling or some other objective, the resulting model, people are calling them, resulting neural networks, people are calling them large language models or foundation models. And maybe the recently, among the foundation models also, the models which has very like very high or very niche capabilities like GPT-4 or Gemini from Google, they are calling those models as frontier models. So they are coining different terms now. Um, so I only talked about pre-training, but so pre-training gives you the base model, which is the main ingredient, but people do a lot of other stuff on top of those things: instruction fine-tuning, alignment, instruction fine-tuning to make LLMs to follow instruction better, alignment so that it is aligned with human values, it doesn't produce toxic thing or negative things. So there is a whole pipeline, but still the base pre-training is probably the key factor, differentiator, and it takes probably for now the most amount of compute and data. But there are this slide is from the Queen 3's training pipeline. So other than base model, they do a lot of these other 4 stages also, with a lot of reinforcement learning to incorporate reasoning capabilities into the models. So this is how, like, this slide is old now, like 2018 to 2022 around. But you see, like, models started with 93 million parameters, and now there are models with more than 1 trillion parameters. So you can see this large language models are becoming bigger and bigger, maybe consuming all the data which is available on internet and other data, and becoming quite powerful. So, and pre-training is one of the key factor, that doing pre-training on huge corpus is a differentiator. So what goes inside this large language model or deep neural network? So for LLMs, the game changer is transformer. This architecture of transformer, which was proposed in this famous Neurips paper in 2017 by Vaswani et al. Second. Yeah, so they propose this transformer architecture. This transformer architecture has 2 parts. One is the encoder, another is the decoder. So, and you can see a lot of the things which are present in encoder are used in the decoder. So it's a pretty kind of a symmetric kind of an architecture. There is some difference in the encoder and decoder. I will talk about this. So this is the famous um, transformer architecture, which is the backbone of current LLM, modern LLMs. People have over the time played with some part of it, like um, adding some different kind of normalizations, or doing some minor changes, but the base architecture is more or less same still. Uh, so I have drawn this transformer architecture abstractly here, and I wanted to show like how does it work. So let's say you go to ChatGPT and you say write a function to print hello world. Uh, how does it produce the output? So the first step when you provide this text is a tokenization. So you because a language model doesn't understand this language of English, it has its own vocabulary, and that vocabulary is based on tokens. So the first step is you break down this text into use a tokenizer and break down this text into tokens. For example, tokens like write, a, word, and then each token is passed into through an embedding layer or embedding matrix, which transform these words or tokens into vectors. For example, 768 dimension vector. So now you went from words to a vector space of dimension 768 of so 768 dimensional vectors, which all are every number in that 768 is a float real number. So each of these x1, x2, x3 are 768, let's say dimension vector. Uh, this vector doesn't contain the position information that this word is occurring at which position. So you add something called position embedding to it. So each vector x1, x2, you add a position embedding to give the encoder the information that what position this word comes in the input text, and then you pass it to encoder. Encoder process it and then pass it to decoder, and then decoder generate the output token by token, and finally generates the desired program that you want. So this is how the things works underneath. So there is an important is there is an encoder, there is a decoder, and things goes like this. I will talk about GPT-4. GPT-4 doesn't have encoder; it only has the decoder of transformer. But for the initial transformer model which was proposed has both encoder and decoder. So, but this is how the thing works. So there is important parts are tokenization, then embedding, you add position embedding, and then encoder process it, give it to decoder, and decoder generates the output token by token. So it's a sequence to sequence model. It takes a sequence as input, it returns sequence as an output. Let's zoom this encoder and decoder even further. So original transformer paper has 6 encoder blocks and 6 decoder blocks. And things like you pass it the input to encoder, and from the 6th last encoder, you pass it the output to all the decoder block, and decoder block decodes the output and generate the final results. So let's zoom in the encoder block. So encoder blocks takes this vector I talked about x1 to xn. Let's say you gave a text, you divided the text into tokens. There are n tokens. Each token are represented as a vector, and then you pass it through an encoder block. Encoder block generally converts that, transform that x1 into z1, x2 into z2. So encoder block is nothing but a transformation unit which transform these vectors in the same dimension vector space. The important part of this encoder block is what is called this famous self-attention. So self-attention is calculate how tokens in the inputs are related with each other. So to calculate the embedding of Z1, it takes the embeddings of all X1, X2, X3, Xn and calculate the embedding of Z1. So in a way, Z1 has knowledge of all this X1 up to Xn. Similarly, Z2 also has knowledge of all the things. So this is how the self-attention works. It for each of the tokens, it takes all the tokens which are in the left or right of the token and calculate the embedding, and then this is how you transform the input. So you saw in the previous slide there are 6 encoder blocks. Each of them will transform the input into uh, um, different vectors and take the information from previous left and right tokens. Um, this is the brief mathematics of it. Maybe I'll not go into that for now, but this is the self-attention thing. Uh, so important thing of that, encoder takes set of vector x input vectors and it returns a set of vector y's The operation of self-attention is little costly. It's order of n square, but it's very highly parallelizable operations. People have worked on to improve the complexity of this order of n square to order of n also. So yeah. So the important thing is that now encoder has encoded the input. Now how does decoder decodes it? So encoder encodes it, pass it to the decoder, the final embedding. Decoder starts with a dummy tokens. Let's just start. So starting the generation, it predicts the first token. So actually it doesn't predict the first token. It predicts the probability over the vocabulary. So every LLM, as I told, has a vocabulary of, let's say, something size 64K, or even there are models with uh, vocabulary size of more than 300K. So it produced probability over all those tokens. And one way is you pick the token with highest probability. Let's say you pick the greedily. So you predict the tokens with highest probability. And let's say the first token comes is deaf. You predict deaf. Then again, you concatenate this deaf in front of start. And then you pass these two tokens now to the decoder and ask it to predict the next token. Now it predicts the next token main, let's say. Now again, you concatenate this main, pass it to again decoder, and it predicts, let's say, this open bracket. Uh, so this is how the decoding works. So note that decoding happens token by token. So if you are producing hundreds of tokens, it needs to pass this, you needs to pass the token 100 times through the decoder. So it's a costly thing. So when you produce more tokens, more computes required, and this operation is not that trivially parallelizable. So the amount of tokens you generate in the output increases your time complexity also and compute also. But but this happens this auto regressively, like token by token. That's why people say that this is an auto regressive generation. Okay. But important is that when you are decoding, decoder only see the previous token. It can't see the future. But when you are encoding using encoder, encoder can see both, like in like left and right tokens of the current token. But decoder only generate left to right. That's why the name is autoregressive. Uh, Another thing which I mentioned is critical is tokenizer. So tokenizer is the piece which transform your input into the language of language model. And every language model comes with a tokenizer. Um, so you can divide the input into different levels of tokenization, like word at word level, character, or subword levels. But if you divided the word level, your vocabulary size will be more, like huge. Your vocabulary size should be the all possible words in the world, which is not possible. If you divide at the character level, the vocabulary will be very small, but then you will lose the semantics of the word. So you'll divide the word right into, let's say, W, R, I, T separately. So you lose a lot of information. So what people do is subword tokenization. So if you heard about this tokenizer like byte pair encoding or word piece, sentence piece, all of them are subwords. So for example, if you use a byte pair encoder, tokenizer, uh, and if you ask it to tokenize this sentence, write a function to print hello world, it will going to divide into these 9 tokens. Right, it will divide into W and RITE. A is simple A. Similarly, function will be function. And so it divides based on the vocabulary. So the tokenizers are also trained. And this is how they divide the input sentence into a subwords. So all the modern famous tokenizer are subword tokenizers. So uh, this is the general recipe. If you want to ask to train a pre-trained large language model, so choose your architecture. So take the transformer. So some models are only based on encoder. Some models are only based on decoder. Like so, transformer has both encoder and decoder. But some models are based on encoder. I'm going to talk about them. BERT is a famous example of an encoder model. Similarly, there are models which are only based on decoder only, which are the current famous model like GPT-4, Gemini, Llama, Quen, all of them are decoder-based model. Um, And there are few encoder decoder model used to be. Now I generally don't see encoder decoder model, but in the past was one of the famous encoder decoder model. So you choose the architecture, then you define your whatever pre-training objective you want to use. For example, language modeling objective or auto like or mask language modeling objective where you mask certain token and ask LLM to predict those tokens. So you choose an objective for self-supervised training on a huge corpus. So you need to collect a huge corpus, and then you need a lot of GPUs to pre-train language models. But most of us maybe don't need to. It's a very specialized and very costly operation. But yeah, this is the underlying way to train this pre-train your language models. As I mentioned, the three famous architectures are only encoder based, which only has the transformers encoder part, or only decoder based like GPT-4 or Gemini, or encoder decoder based like the original transformer part. But the famous one currently are encoder only and decoder only. Encoder only are BERT and robot and all those models which are used to create embeddings of the sentences, and all the other famous models which you use like GPT-4, ChatGPT, Llama, all of them are decoder only model. So this BERT model which came in 2019, which was the famous model and which started this revolution of large language model, it was only the transformers encoder part. And so multiple stacks of encoders are stacks one on the top of another. Uh, and as this is only transformers encoder block and uses self-attention, so it's a bi-directional model. So every token sees what comes in the left, what comes in the right, and it was trained on two uh, pre-training tasks, uh, which is one is mask language modeling, another is next sentence prediction. So these are the two tasks it was trained on. So they collected a lot of sentences or text from a lot of corpuses, books, and others, and they created these two auxiliary tasks. So one task is mask language modeling, where you have a sentence like the ISB is located in Hyderabad city. So you mask certain tokens. Let's say you put mask one here, mask two, and mask one, you know the value is ISB, mask two value is Hyderabad, you know. So you pass it to the LLM and ask LLM to predict the value. You compare with the ground truth and you propagate the loss, and this is how you train. The second task is next sentence prediction. You give a sentence A and a sentence B, and you ask model whether sentence B follows sentence A or not. It's a classification task. So it's just a next sentence, whether this sentence comes after sentence B comes after sentence A or not. So this is the two task it was trained on unleveled data. And this, when it pre-trained, it became the BERT, the famous BERT model. And generally, they trained it on at that time on 800 million words collected from books corpus plus 2,500 million words from English Wikipedia. And they released two different variants of BERT, BERT base and BERT large. BERT base has roughly 1 million, 110 million parameters, and BERT large 340 parameters. So generally, these encoder-based models are good to create embeddings of the text. For example, you have two pieces of text and you want to find out whether they are similar or not. So what you can do is you can pass those two sentences through BERT, get an embedding vector for those two sentences, and then maybe do a cosine similarity between those two sentences and find out whether these two sentences are similar or not. The other famous thing I told you is decoder only model, which is the backbone of GPT family and Gemini and other models. Uh, it only consists of the decoder part of the transformer. So there is no encoder, and it is trained on standard language modeling objective. I told you about what is the next word like predict. So how does decoder training happen? You give us, let's say, first token. In generally, when you do training, you don't give empty like start token. You generally give 2, 3 tokens from the corpus. For example, you can give the movie was. But in this example, let's say I start with the dummy token start, and I ask model predict the thing. Now this model is predicted the, I know the first word is also the, so there is no loss, model is correct. Let's say I give this prefix, start the, ask model what should be the next token, model predicts match. I compare match with, okay, my token was movie here, so there is a mismatch, and I propagate a cross entropy loss, and I do a back propagation um, of that loss. And this is how the pre-training of GPT, like decoder only model happens. Uh, and let's say then again you pass the movie, correct thing, and ask what is there. It predict was, and it was here also. So you say there is no loss, and you don't propagate any loss. So this is the way these GPT-based decoder models are pre-trained on a huge unleveled corpus. And this is how the GPT family evolved over the years. So it started with 2018 with 110 million parameters. Then 2019, 1.5 billion parameter GPT-2 came. Then came GPT-3, which was a huge model of 175 billion parameter trained on roughly uh, 45 terabytes of text, and it came in 2020. Then GPT-4, ChatGPT came in 2022, and recently GPT-5 came in 2025. And you can see the scale of the model is increasing as the time is progressing. So, and this if you take this table from GPT-3 paper, GPT-3 paper was trained on 3 billion tokens of the text, uh, and roughly if 10K GPUs and likely for 12 days. And for one training, roughly the cost is $4.6 million. So it's a huge process and huge investment is required to perform this scale of training, pre-training. So one thing is, what does is all this scaling of compute and text like tokens is buying? Why people are crazy um, and increasing the model size and compute to train those models. So this scaling is bringing a lot of emergent abilities, like what there are a lot of abilities models are showing, which was not present in their pre-training corpus or any other training data which they use. So models are able to solve new tasks. So one example of emergent ability is in context learning. So what I mean by in context learning is, so if you see traditional fine tuning, what you do, you if you want to add a new capability to your model, what you do a supervised fine tuning. So let's say you want to teach model English to French conversion. So like you'll provide English text and you want French output. So what you'll collect certain example, let's say example 1, 2, 3, and for each example there is an English sentence and corresponding French sentence, and then you you do a fine tuning of your model. So you will do a lot of back propagation gradient update. You update the parameters of the model. Once the training happens, then you give a new sentence of English in the test set and ask model to predict. So this is the way traditional fine tuning works. But when you train this model on huge data, what people observe is this emergent ability of in context learning. So what is in context learning? So you pre-train your model on, let's say, this unlabeled corpus, but now you want to do English to French task. You don't need to fine tune your model. You just give a task description that I want to translate English to French and provide the thing like cheese, translate it to French, and model generally is able to translate. So this is the zero shot ability, like you don't provide any example. Model is by default able to solve the problem without even a particular fine tuning on the task of translation. Model knows how to do that thing. So here no fine tuning is required. You just ask model to provide an instruction and the input, model produces the output. Uh, the few short version of the in context learning is that you not only provide the task description, but you also provide certain examples. Uh, like 3 examples you provide from English to French translation. And then, so these are the few short example. And then you ask model okay, now cheese, I'm giving you cheese, like translate it to in French. And this is all happening without any fine tuning. So this is what happens when you go to ChatGPT, you provide certain task description uh, and maybe sometimes some example, and model on the fly learns the task and solve your problem. So this is the ability of in-context learning. And generally, bigger models showed better in-context ability compared to the smaller model. Like it is very hard to find good 4 to 8 billion models which has very good in-context learning ability. Generally, models of more than 12 billion or even further show very good in-context ability that you provide certain example and model learn the task on the fly. You don't need to do fine tune the model on the task. Still model learns your new task and performs it better. Um, I don't know if you know about maybe Hugging Face, but Hugging Face is a hub or a go-to source for language models. You can go there, you can download those models. People, companies upload their models and all the recipes, like how to use those models on Hugging Face. So Hugging Face is a hub where you can go and fetch these models. So the key takeaway till this point is that transformer is the main building blocks of LLMs. And LLMs generally comes in three variants: encoder, decoder, encoder only, and decoder only. But currently, the most famous ones are encoder only and decoder only. And the scaling of large language model to huge number of training data and compute gives you better um, emergent ability in the model, and they becomes a better uh, depiction of the world they are trained on. Okay. So yeah, this is the basics of large language model I wanted to cover. Any question till this point? I will be happy to answer this. Uh, oh, there is a question. What is your opinion about data poisoning attacks on LLMs and their effect in future development of data? Yeah, so I don't work in security much, but one thing is that when these models are trained, they are their data is filtered very thoroughly um, during for pre-training and other things, and alignment is also done for human value. So still, yeah, this poisoning attacks can happen, but yeah, uh, people they are discovering a lot of new things to mitigate, and adversaries are also finding attacks on the LLMs. Any more question before I continue to some applications? Okay. Okay. So one famous application of LLMs are retrieval augmented generation, which is commonly known as RAG, and which we are also very much interested in IBM. Uh, so what is the task of RAG? So let's motivate. So whatever till this point I talked about LLMs, they are parametric LLMs. Like by parametric, I mean their knowledge in the LLMs are encoded in their parameters. And and they are very like good like creative writers. For example, if you ask narrate the story of rabbit and tortoise in a pirate style, it generates a very compelling story in the pirate style. So they are very good creative writers. Uh, if you see ChatGPT's or GPT-4's performance on a lot of these exams, like essay, SAT or other ZRE and something, they score huge marks on those. So their performance on exams are also good. So they are in general very good in a lot of tasks. But one problem with LLM is they hallucinate. And the problem is that when they hallucinate, it becomes very difficult to find out whether they hallucinate or not, because they are very good writers and they know a lot of things. For example, if you ask what is the use of PMI in NLP, it produces a very good description of what does PMI, point-wise mutual information, means. Now let's say we ask, can you give me citation of above example? It also generates certain citations like, okay, these are the citations. But the problem is that when you go and search for those citations, sometimes happens that those paper doesn't exist. So for example, when we ask this question, um, um, it generated this citation point-wise mutual information for language modeling. We search in Google Scholar and we don't find exactly the same citation. So they hallucinate, and they hallucinate with a lot of confidence. uh, so for example, I thought second example also, like second uh, source which the ChatGPT provided is also doesn't exist in the Google Scholar. Uh, so hallucination is a big problem. Like there are cases has been submitted on people who uh, submitted ChatGPT based citations. So hallucination is a critical problem with LLMs, because the other thing is verifiability. Like somebody needs to verify the output, like, and how to verify whether they produce the correct output or not. Like, can you um, so for example, if you go to ChatGPT writes this disclaimer at the bottom that ChatGPT can make mistakes, consider checking important information. Um, so for example, in this example, even not the title, even the link it produced, the link was correct, but the paper was different. It says point-wise mutual information for language modeling. This is the URL, but this URL, if you go, this is the different paper. Uh, Another limitation of ChatGPT or these language parametric language models is knowledge cutoff. So they are pre-trained on a corpus till certain point in the like timeline. Like they collect all those data, let's say till 2022, and then they train. But what about the events which occur afterwards? Okay, so there is a knowledge cutoff, and they don't, like, if you ask a question on a future, they'll give a wrong answer. For example, we asked who is Adit Grover, where does he teach? Now Adit Grover was a IIT Delhi student. He is currently he joined UCLA, but ChatGPT is returning. He's a student, PhD student at Stanford, which is, so its knowledge not up to date. So, so as I told you that how does parametric LLM work? So when you train on this auto-regressive, you provide prefix of a sentence, the capital city of Ontario is, and you ask model and you teach them the capital is Toronto. But at the test time, when you provide the capital city of Ontario is, it produces the probability over a vocabulary. It doesn't say that it's token. It says it's produced a probability over the whole vocabulary with different levels of confidence. And this is how they work. And sometimes they put a lot of mass on their incorrect examples. Now, how does RAG come into picture? So, for example, if I ask you, let's say, in your institute, you want to build a question answering system so that when a new faculty joins, uh, he can ask certain questions about the policy of the institute, uh, or like whether the institute supports provident fund or NPS, all those information, or how to read certain lab, or like, so let's say your institute has those documentations. Now, how can you design a system, questioning system over that LLM? So if you take a out of the box LLM, that LLM will not going to have the knowledge of the documents of your institute. Okay. So one way is you need to fine tune on your documents, but which is very costly. Another thing is RAG. So what I mean by RAG, so if you think of this analogy, so how does parametric LLM works? You give a query, LLM has learned certain knowledge in the pre-training, it returns the answer. But RAG is the uh, analogical to this, where you give the query to LLM, but also you provide the document also along with the uh, query, and ask so LLM to answer by looking in the document. It's more like an open book exam. So parametric LLMs are closed book. You learned in your pre-training stage. Now you can see the corpus again. But in the open book setting, model is learned during the pre-training, but it's also equipped with, you have given the tech documentation at the time of testing or inferencing also, so that when you are doing query, model can consult the books or the docs and can give the answer. So if you want to design a question answering system for your um, college or institute, you can have the policy documents and you can give those documents to the LLM and tell that, okay, when somebody is asking the question, look in the document and then give the results. And this is how, without fine tuning, you can make a question answering system using this pattern called RAG. So how does RAG in general work? So let's say you take the documents of your corpus of your, let's say, institute, and then you create an index, document index. So you chunk your documents, feed into a database. Generally, these DBs are known as vector DBs. They store paragraph and corresponding embeddings of those paragraphs. That's why they are known as vector DB. So when a new query comes from a user, you search for the document, you search the document index. Document index will return certain passages, and then you will. So this is the retrieval stage of the RAG. R stand for RAG, retrieval. Then you pass the query along with the retrieved passages to the LLM now. So you are saying, LLM, this is the query, this is some useful passages. Now give the answer, and LLM returns the system response. So this is the famous RAG pattern or RAG based LLM architecture. So it has two part: retrieval, where you retrieve certain passages, and then there is a generation part where you generate the output. So it simply uses like combining the existing models. So for retrieval, you can use off-the-shelf retriever like BM25 or ELSER. Lot of models are available for retrieval, and similarly, you can use your favorite model which is available as a generator. So, and you can use a lot of tools which like LangChain and other to create this RAG-based architecture in very, like, these are very simple to, you can write 100 lines and maybe create a RAG-based pipeline for, let's say, question answering over your policies of your institute. So this is one very useful use case for LLMs, and this mitigates the problem of hallucination, which I started like motivating this. Like when you provide the documentation, you are asking LLM to ground the conversation based on these documents. So there is less chance of model now hallucinate, and you can even ask model when you are providing the answer, even cite that this answer is lying in which part of the passage, where it is lying. So the verification of the answer also becomes easy. And also it helps to solve the third problem, which I told, knowledge cutoff. When you are providing the passages, you can give the new knowledge. Now the new knowledge you are giving as an outside. Now you are not feeding that new knowledge in the parameters of the models. So this knowledge is outside the parameters. So even let's say the policies of your institute changes in the future, you can bring the new documents again, index it, and again, without updating the LLM, you can have this RAG architecture. So it mitigates all this hallucination, verifiability, and knowledge cutoff problems. So we in the IBM works extensively on RAG. So we published a paper last year in NACL, which was even improving the RAG system on very domain-specific documents. So in IBM, there are a lot of customers with very domain-specific documents. So how to improve the capabilities of the RAG system? So RAG system, one problem still exists is that when you give a query to a retriever, it searches the document index, but many times it also happens that it retrieves, let's say, top 5 passages, but top 5 passages doesn't contain the answer. It retrieves wrong passages. So then what will happen? If you provide the wrong passages to LLM, it will going to produce a wrong answer. So in this paper, we injected the knowledge in the LLM. So we take the domain specific document, we create a lot of question answer on using those documents. We fine tune our LLMs. In this, we are fine tuning the LLM, and then we plug that LLM into the RAG architecture. So even if the retrieval fails, we expect that LLM can still can answer the question based on the fine tuning on the domain data we did. So this was last year's paper we published. Another application which we are working on extensively in IBM is tool calling abilities. So uh, uh, we want to improve the tool calling ability of IBM's Granite models. So IBM has this model called Granite model series. We want to improve the tool calling ability. So what is the motivation of what I mean by tool calling? So let's say I again ask you a question that I want you to design a chatbot for your institute student. So that should have a conversational interface and should support like institute rules, policy, related query. Like some student can search for course, add a course, or a drop from a course, or pay fees. So how to design that thing? So some of the things here is not only querying the policies. Here you want like they can pay the fees. So if they can pay the fees. They need to access certain database where their information is stored. Once they pay the fees, the database should be updated that the student has paid the fees. So all these operations should be provided. So one way to implement this kind of a conversational facility is if you can create tools or specialized functions for all these things. Let's say you create a functions to add a course or drop a course and provide those functions to LLM. Ask LLM, oh, these are the functions. When a student type a query to add a course, ask relate in informations about the what necessary information from the student, and then call these functions which I'm providing to you. And this function will go into update the database. Uh, so LLM needs to know how to call the tools, when to call the tools. So this is the ability of function calling or tool calling, where you provide LLMs with certain tools and you ask LLM so that they can call those tools. So this is the uh, general architecture of tools. So there is a model or LLM. You provide LLMs with certain tools, definitions, and when a user comes, is it asks a it gives a prompt or a question or anything. Prompt goes to an application layer and then it goes to the model. Model identify a function. Okay, this function I need to call and these are the parameter I need to pass. Then it passes the function call to the application. Okay, call this function with this parameter. Application calls the function, return the answer to the LLM, and then LLM consume that output and then respond to the user in a maybe more natural way that, okay, this is the answer to your query. Like I'll give you an example. For example, um, so let's say there is an LLM with you and you provided these tools to LLM. So by providing tools to LLM like payment status, payment date, what I mean, you provide this kind of JSON description of the tools or the function to the LLM. That okay, there is a function retrieve payment status. It takes this arguments and return certain things. And there is an implementation of that function lying somewhere in the application, but you only provide the definition, the tool description of the tools to the LLM. Now, let's say somebody comes and says, what is the status of my payment? So my transaction ID is this. So LLM needs to figure out among these tools, which tool I need to call. So it figure out, okay, I need to call payment status and I need to provide the transaction ID, which is T101. So it generate this tool call, it passes it to the application. Application calls this tool payment status with this transaction ID, get the entry from database, and then this paid thing, this answer is returned to LLM, and then LLM provide more natural looking answer to the user. According to the information available, your transaction has been paid. Is there anything else I can do? So this is the ability of the tool calling or function calling. And I think you have a next section on agentic thing. So agents, when you design agent using LLM, the one ability you require most is the ability of tool or function calling. So tool and function calling are synonymous thing only. So when you design agent, LLM needs to know when to call which tool, or even sometimes needs to call another LLM or not. So model should have this good ability of tool calling to become a good agents. Okay. So, so currently we are training, we are creating a lot of data so that we can fine tune our Granite model on this tool calling ability. And to train this model, we requires a lot of data. So how does the data for training this model looks like? So for example, user says, what is the status of my transaction in this? Then this is the user query. These are the tools. Then assistant should make a tool call. Then tool call should execute, and then assistant should respond to the user based on the tool response. So this is an example of a single turn where user asks something and assistant respond. But we want multi-turn ability where user and assistant, which is an LLM or agent, interact over multiple turns. So with there we require this multi-turn tool calling data. We require a lot of data with assistant clarification. There are many cases where user will not going to provide all the information, so that agent or LLM should have the ability to clarify the things from user. There are multi-step tool calling. For example, a user can ask, I want to book a ticket from New York to LA tomorrow. Now to book a ticket, there needs to be first needs to call a tool called search flight. So LLM needs to internally do a planning and figure out, to book a ticket, I first need to do a search flight and then I can book a flight. So it do a search flight first. It gets the output of such flight. It returns output to the user that I found two flights from New York to LA. One is Delta at 9 a.m. Another is at 12 p.m. So now user says book the Delta flight. So now LLM do another tool call for booking and then goes to the user. So to fulfill this user request, LLM needs to do multiple tool calls, not single tool call. And then LLM has to do this implicit planning that to call a book ticket, I need to get first search ticket to get the IDs of the flights. So this kind of data we need to make this LLMs good at tool calling. So this is again an active research of area. So yeah, these are the two things we are currently working in IBM. At least I am working in IBM. There are other things which my colleagues are working. So yeah. So yeah, that's it's all from my side. We can take uh, questions if you have anything. Yeah, anybody has any question, please feel free to ask. Uh, so the question is why they hallucinate. So they hallucinate because as I told you, they predict the probabilities, and it's not always the possible they put the right mass on the right things, and there exists conflicting information on Wikipedia and everything. So when they are training, they get conflicting information which disturbs their internal conflicts, and they put sometimes incorrect probability on things. uh, so this this question lies to the internal mechanism how the LLM works, but which is very difficult. People don't have correct theory, like how they store. Like you are giving this trillions of tokens and they are compressing all this information inside their parameter. How they storing that information, it's not clear. And the other thing I talked about, like cutoff date. Maybe today you ask LLM who is the Prime Minister of India, they'll say Narendra Modi, but it might happen that some of the LLMs can give that answer wrong because they have seen in the text that Manmohan Singh was also the Prime Minister, so they can get confused. So yeah, so it's not very clear why they hallucinate, but hmm. Yeah. Please go ahead. Uh, Somebody was saying something. Okay. The other question is, can you just tell that in your paper how the answer of created questions will be detected as correct if it is says the answer from wrong paragraph? So in our paper, uh, are you talking about RAG in general, RAG architecture, or like the paper we published? Okay. So here, what we do is we use another model. Like we did all experiment on Granite and Llama model, but we have a corpus, text corpus with us. We created question answering using mixtural models. So we created a lot of question answer pairs from that using a mixtural LLM. So we prompt LLM, we chunk the text and we ask LLM to create question and corresponding answer given this information. It can happen that LLM can create a wrong question answer, like even we provide the information, but it will be very less and it will be treated like a noise. So this is how we create question answer pair. And then we fine tune our LLMs on those question answer pair so that it knows the information about the domain. And then we use the domain specific LLM inside the RAG architecture. So if you see here, instead of GPTX, you replace with our fine-tuned model on the domain specific corpus. So now model is uh, two ways to know, like, so when a user gives query, there is a retriever which will going to retrieve the passage. Even if retriever fails, we have trained the model and we train intelligently. We train model both ways. We train model to train when the passages has the answer, then give the answer, and when passages doesn't have the answer. So we train also like that, where we provide all the incorrect passages and we force model. Now this time you look in the parameters of your memory of your parameters, and then give the answer. So we intelligently train that way so that model learns when to rely on the information provided in the passage and when not to rely on it. Okay, so you're saying RAG. So uh, in RAG also, it can happen that if a retriever fails, then model will going to generate an answer most of the time, and it will going to provide a wrong citations. So yeah, those things still happens, but I'm just saying that RAG is a one way to reduce that phenomena of hallucination or giving incorrect citations.
Participants, any other question?
Thank you, sir, for your
I
answer.
think any other questions? I think that's it, sir. No
Okay.
other questions. Thank you so much, sir, for your time. This was indeed a very insightful speech of yours. We are really grateful that you could give us some time for this talk. So this is a small token of appreciation from our end. Kindly accept it, sir.
Thank you. Thank you.
Thank you so much, sir.
Thank you. Thank you. Bye.
Dear participants, the meeting ends here. You may leave.